Alrighty. We are live for day 14 of Edmund Code, 15 minutes to go. And until then, for a little warm up, I think I owe it to myself to refactor day 13 a bit. So let's look at what we have. We have a little point class that we're using to represent both the buttons and the prize locations. And this is our parsing code. We just decided to go 3 passes, which is fine. Makes it easy. And I had this winnable method, which, yeah, this is a necessary condition, but not sufficient. And actually, let's just give that a test real quick. I want to see kind of what the difference is. So when we've taken machines from part 2 and see how many of them there are here. And we could also do a count of winnable. Whoops. Okay, here we go. Yeah, so that thinks there are 264 that are winnable. Okay. I am curious about that. I'm going to leave winnable up, but I'm going to explore which ones are not winnable, even though they actually, which ones I consider not to be winnable, and see if we can gain some insight out of defining a winnable function. Okay. So let's go back up here to the top. Yeah, we parse our machines. We have the winnable function. We had this before prize method, which we were using it as a filter. It's not even necessary for the part 1 brute force, which, we're going to delete that part 1 brute force anyway. So yeah, let's go ahead and just delete that. Winnable, we will leave. This cost calculation. I kind of like the idea of having a separate cost calculation. Yeah, separate from the number of points. Okay, so we just delete combos. I guess now we do like combos 3, which I guess we will rename. Or cost 3 rather, cost 3. Cost 2. Right. Okay, well, that still works. This stuff I don't believe we are using. We might use it later in our new winnable, so let's import them in there. Yeah, I think cost we will rename to solve, cost 2, and we'll change the type. So rename to solve, and we'll give it this method signature. Okay, and we will dig more into that solve method later. But for now, let's delete this. This cost 3 is basically cost 2, but rewritten in such a way that I could test more pieces of it individually. Um, and yeah, we are now returning a tuple in the solve method. This is a test that we, I guess, no longer need because we don't have a brute force implementation. But I'm realizing maybe it'd be nice to have that if we're modifying our solution. Okay, so we flat map solve map cost, that's sum. Cost operates on a pair of ints. It should take a pair of longs. Okay, sure. Map cost, not sum. And it should return a long. Okay. Okay. So part one and part two basically look the same. I'm just gonna move them next to each other. Let's put these machine definitions next to each other too. All right. That's looking better. Wait, is that still accurate? Did I somehow change something? Oh, right, because we multiply by 3 here. Here, we just want the tuple. Okay. Okay, everything still looks good. Now we had a bunch of debugging here that we no longer need. So let's take out those print lines. Let's see. I'm not entirely sure these filters are necessary. Making sure the times, well, I think they actually might be necessary. This should fail. No, it doesn't. Hey, Eric Wassel, welcome back. Thank you, thank you. I have a question about the theme and story of Advent of Code this year. And so I've noticed every now and then kind of subtle references to past years. Is that like a theme throughout the whole year this year? Is like a tour of past Advent of Code problems? Oh, it's a story question. No, no puzzle spoilers. Okay, okay, fair. It is spoilers. Ah, okay, okay. Well, the fact that it's spoilers is spoiler enough. There's a link to the previous day's puzzle on each day. Oh my god. Well, it was subtle enough I didn't notice the link. Rises from claw machines. Oh wait, no, no. Arcade lobby. Oh, okay. I mean, I was noticing that some of these were familiar. This one wasn't familiar to me because I hadn't solved it. But the ones that were from like the last 3 years, I was recognizing. Oh wait, no, I have solved this. Should have been familiar. Hexagonal tiles. I mean, this seems fun. Yeah, I probably solved it with like a three-dimensional coordinate system. Cool. Okay. So solve all the previous year's problems and I'll have an edge. Did I get part two from yesterday? Yeah. I mean, I wouldn't say it's math heavy, because you have two equations and you solve with you can just solve with substitution like we do in middle or high school, right? Um, but geez, did it take me a while to do that? I mean, okay, ultimately, the problem was that my math, which I kept checking and rechecking, was fine, but I had a little plus sign here, right here. And a viewer noticed it and let me get to sleep an hour earlier because it would have taken me a while to notice that. I just wasn't trusting my math, I guess. I kept rechecking it. Okay, we don't need these print lines. Apparently, we didn't need to make sure those are positive. I guess those are always going to be positive. I'm not sure I'm convinced of why. I mean, okay, if one is positive, hmm. Yeah, I'm not sure why that's always positive. I'll give that I'll make that to do for myself. Um to do. Why is it always positive? Little math puzzle for myself. Oh, we have 3 minutes. Okay, I'm gonna keep doing this. This winnable function. I want to explore that. Well, decreasing the search space might be more work, honestly, than simply finding the exact, doing a direct calculation. Okay, so let's do ANDS one or I don't know, machines that count winnable. Actually, let's put this up here next to the winnable that we're testing. Okay, machines that count winnable compared with machines that flat map solve that size. He designed A13 completely with pencil and paper, which is rare for an AOC puzzle. I remember one a few years ago that I did solve with math, pencil and paper, about like shooting something. Um, yeah, it's like trajectories of things, and I just straight up solved that one with math, and I got a pretty good time on it for me. Okay, I want to check. So machines that count, or let's filter them. So I want all the machines that can be solved. So solve m dot non-empty. And I want to count how many of those my algorithm here considers winnable. That count winnable. I guess I also just want, well, yeah. And that should be 174. Okay, so it is indeed necessary, but not sufficient in its current state. Wait, 1 minute left? Oh, my alarm was muted. Okay, thank you so much. Good luck, everyone. Day 14. Here we go. Someone mentioned Kramer's rule in stream. Yeah, Kramer's rule. Yeah. Actually, let's Wikipedia that. I gotta read up after this. I think it might be right. I can't remember. Okay. We have positions and velocities. Ooh, great. Needs to use a bathroom to make your list. Okay. X and Y are tiles per second. Okay. Positive X means the robot's moving to the right. Y, positive Y means down. Cool. That's already how I'm do it. For maximum bathroom security, they can teleport. When a robot would run into the edge of the space they're in, they instead teleport to the other side, wrapping around the edge. Okay, okay. So after 1 second, velocity 2 and -3. Yep. And then, yep, yep. Okay, so we just mod that. To determine the safest area, count the number of robots in each quadrant. Quadrant. Wait, what is the area, though? Is it just a bounding box? Number of robots in each quadrant after 100 seconds. Robots are exactly in the middle. Don't count as being in the quadrant. Okay. Multiplying these together gives a total safety factor of 12. Multiply each quadrant. Okay. What is the area, though? The area outside, okay. What is the size of the area? Within a space which is 101 tiles wide and 103 tiles tall. Okay. 101 by 103. And so we can just parse the positions and velocities separately. No, we'll just keep them in there. So in case last robot, pause is a point and velocity, we'll just call it P and V. P and V or see that point. Okay. And we parse this input dot collect. Geez, I hate this autocomplete sometimes. So case P equals, say, px py, b equals vx vy. It's trying to do too long because of the day 13 code that is open. So val robots equals that. And I don't know what you to list this. It's already a list. 2020. Okay, it seems like we failed to get the input. Here we go. Okay, so that's parsed. No, not quite. There's no comma here. Okay, that looks good. That looks good. And I think in my point class, I already had utilities for handling position and velocity, right? Velocity? Nope, I guess not. Oh, we do have an inbounds method I should be using. Okay, now we had an area, so val area. It's not a bounding area. We have basically, I don't know, is the leftmost 1? It's 101 tiles wide. So let's just say 0 until 101, and then 0 until 103. Okay, and then we need like a move method on the robot. And we do P plus V, but then now that position needs to wrap. So def wrap a position in, I guess, a given area. Okay, so we get a new point. So the new X Okay, some of them might be moving negative, which means the modulo gets annoying. I don't know if just p dot x. I don't know if it's just going to be that. Let me think about that. Let's just do a test. So let's say we had -2 mod 100. Oh, we got to import the area too. This is going to be -2. We could add 100 to it. We can add 100. So p dot x plus a dot width mod a dot width. Um, Same with y, and we just return that point. Okay. So after we move, we then do have to do that wrap. So p plus v, um, I guess this is within area A. So we have p plus v, no, wrap. So we're wrapping that inside of our area A. Okay. Velocity is in terms of per second. Motion of the robots. Okay. So yeah, we just move them repeatedly. Robots.map. I know, let's take r.move in our area. But we have to do that so many times. Let's iterate. So iterator.iterate. So starting with r, we do that move within the area. And after 100 seconds, so we drop the first 100, drop 100 next. Okay, so now we have new, we have like final robots, and that map, we're just gonna take the position. Now final positions. Okay. And we could also just multiply the velocities by 100. Ah, yes, I could totally do that. To do mult v by 100. Okay, now we get the quadrants of our quadrants. Area, let's see, 0 until 51. And I guess 52 until 100 or 101. Yeah, okay. Or no, hold on. Let's just do this with, in terms of area. So area dot width over 2, right? So val mid x. And since that's odd, we're going to do 2 mid x. Let's do mid y, same thing. So we have 0, 2 mid y. And then we have area mid x plus 1. plus 2. Yeah. Okay. Autocomplete gets the message. Um, yeah, oh, you can't put that in there. That works better. Okay. What does that look like? Okay, I think that looks fine. So quadrants.map. Um, so this a two set. Dot two. Oh wait. Can two robots be in the same space? Yeah, I'm just keeping it as a list. Um, final positions dot count. So given the Q quadrant, Q dot things. Okay, and then we take the product of that. Ends one dot product. All right. Ooh, that's large. Robots dot size 500. Yeah. Okay, that's weird. What's the size of final positions? That should also be final positions. Whoops. That should be 500. Oh wait, yeah, it's a product. Okay, it's gonna be big. Let's just do a map too long in case. And 227,584,000. Okay. Oops. Um, so that's wrong. I don't know. Let's take these and just do the counts. 112, 125, 127, 128. Seems fine. And the sum could be less than 500. Yeah. Um, do our quadrants look right? Oh no. So 0 to 50. We do we have a nasty part too? 0 to 50, right? And 52 until 101. Our quadrants are wrong. We should do 0 until 50. Yeah. So 0 until mid-x. And all these plus 2's become 1 plus 1s. Plus 2, plus 1. Up. And again, all these 2's become untils. Okay, that should be better. Let's try that answer. 214109808. Okay, part 2. Similar to the ones built in use of North Pole. If they're the same type of robot, they should have a hard-coded Easter egg. Very rare. Most robots should arrange themselves a picture of Christmas tree. There's a fewest number of seconds that still have to display the Easter egg. Okay, cool. Well, luckily, I have a way to draw already. Wait, what's going on? Okay. Um, So for all the robot positions, okay, val, or we'll do def, we'll do states, iterator of a list of robot, and it's just this. In fact, we can do yeah, I guess we're doing this in a different order. So you start from the robots, and in each step, we map and we move within the area. Okay. And for each state, we're just going to draw. So state dot for each. And this state is a list of robots, right? So we get positions. P's equals s.map p. And then we have like area.draw. Okay, given a point. Let's make this a set. To set. Okay. We draw that, otherwise that. And then we take the number of steps. So let's take our states and zip with index. Where's my code completion? So we're going to print line. Well, okay, we're going to print line that first. Let's say state I. And then we draw this. And after all that, let's just do an empty line. States, okay. And now this is a case where yeah, this is a case where we copy the worksheet output. It's not worksheet output. Failed to evaluate. Timeout. What? Oh, wait. We need a limit on our states. So let's do states dot take 100. Okay, so I guess we start by drawing them. And if it's a number much larger than 100, then you'll have to use some kind of cleverness to search for like big blocks of arrangements. Okay, now we're scanning for Christmas trees. You pointed. Awesome. Great. Eric, what's a trick in this day too? And then 1 minute later, like you pointed. Okay. So either you figured a trick or there was no trick and you're fine. I'm going to zoom out just a little bit. Okay, I might have to find a state such that we have like a solid block anywhere in there. Zara pointed as well. Cool. Part 2 is anti-LLM. Yeah, it sure is. Have you seen those videos on YouTube of someone like trying to get ChatGPT to draw a circle? in like ASCII. Oh, okay. We're seeing pattern. Wait, we're almost seeing patterns. Maybe it's a multiple of 11. 11 was weird looking. Okay. Let's look at state 22. State 22. Maybe. I might go on my gut feeling and search multiples of 11 instead of like doing a computer search for like blocks. Yeah, I scrolled through the first 100. Okay. Let's cheat. So, our states, let's just move states here closer. So, move. Let's just multiply each robot's velocity by 11. Dot map r to r dot copy, where v equals r dot v times 11. Let's take a look at that. Wait, we can't do that. Maybe it's not member point. Def plus was right here. Was this like not compiling or something? Inside point.scala, is there compiler errors? No. Okay, well, let's just copy this in then. Extension on point. Okay, so this becomes p.x and p.y. Okay, let's take a look at those. MX, copy worksheet outputs, or is it multiple of 10? Okay, I don't know, let's scroll back to the top. That's weird. I'm not seeing the same one. Maybe I have to multiply it by 10 rather. Yeah, because state 11 is after 10 steps. Okay. Multiply by 10. And we copy that worksheet output. No, okay, we gotta do something programmatic. Okay, so we take our states, states dot filter, and let's just go back to normal states here. We can take a guess that there's a trunk. Right, so somewhere in the middle bottom. Um, okay, yeah, let's just do this. That contains maybe not 0.5050. 50 should be right in the middle, right? So 50 and 75. I guess for each state, um, map p.toSet val p's. Okay. You don't understand what part two is asking for today. You didn't have to check the Christmas tree. Checked all inputs manually for Christmas trees appearing by chance before the intended time. That tells me that maybe the intended time is pretty long. But yeah, exactly what I was thinking, Brett. You could start the Christmas tree and work backwards. And there's probably a period, which I'm sure there's a way you can just check that programmatically what the period would be. Um, oh, I mean, least common multiple of all the x's times the least common multiple of all the y's, basically. So 5076. And let's just check, you know what, let's check the ones to the side. So let's do 5175 and 4975. Okay. So we do that. And then we take 100. And let's check through those. Oh, sorry, this is like super zoomed in. Can't see my code. I'm sorry, but does a Christmas tree, what does a Christmas tree look like? It looks like a Christmas tree. You have to develop a heuristic for finding something Christmas tree-like. Your tree was sideways? Did you mix up X and Y again? Um, failed to evaluate worksheet. Uh, okay, I mean, maybe we should be going from set to set. The thing is, I'm worried about robots overlapping positions. I think at some point robots overlap positions. I can't use sets of points because then they should unoverlap afterwards, right? Okay. No, it's not printing. We're failing to evaluate. This filter is too. Oh, okay. I'm not finding that many for that. Let's just take one for now. Then we can bump that up to 10 afterwards. Let's see what this prints. I mean, state 0, it should. Let's just take 3 of them. No. So that timed out after 30 seconds. Really? Okay, I guess there's no trunk in the middle. Let's go up higher. No, maybe let's go up lower. And let's search for a trunk by doing a vertical check. Or actually, we could check quadrants. Oh, we could check the quadrant sizes. And we could be like, there should be roughly, I don't know, there should be roughly triple in the bottom 2 quadrants as there are in the top 2 quadrants, right? Yeah. Quadrants is kind of a hint for part two. Okay, so we'll just take we'll do a take one here. Um, so our quadrants, we had, I know, the top two quadrants first, right? Um, so quadrants dot take two. Um, I guess we still want p's. And I guess we want to zip with index at the start. Okay, so let's just do this within here. So in our filter, you take I don't know how long this is going to be. So we're going to make this an infinite search, but we're going to take the first thing. Quadrants, and we zip in with index. And filter. And we have an S and an I. And in our printing method, we could just have as a points an I. Right? Yeah. And then val top half equals quadrants take two. Dot half is quadrants drop two. Okay. So top half. Now we're gonna map. Take that quadrant. P's count quadrant contains. Sure. And then we do the same. Maybe we don't two set this just yet. Because we're using quadrant contains. Okay. Um, I guess we're trying this. Well, no. So we want to keep it if. All right, let's get the bottom half too. So dot half, dot map, count, and dot sum, dot top count, and the bot count. And top half should be within. Let me think. So bot half should be roughly triple, right? Let's do a range. So bot minus, how many robots are there? 500. So let's give a wiggle room of 50. Yeah. So bot minus 50. Import AOC dot control. So we're gonna do an interval from bot minus 50 to bot plus 50 and check that contains top. And if it does, then we make this set here. Okay, I think that might work. After that, let's just take one such potential tree and draw it. Wait, what is S? S is our states, right? This is a list of robots. What's the problem here? Peas is not a member of the list. Oh, wait. That two set. Okay, there we go. Okay, we found a state. State zero. State zero already has that ratio? No way. Really? Okay, well, let's print these numbers. Top and bot. Oh, what's going on here? Okay, let that run. Top has 225 and the bot has 231. Oh, well, that doesn't make sense. So our filter says that bot minus 50, like the bot count, plus the bot plus 50, which I guess in this case, our ranges is too wide. Oh, wait. We need to divide that by 3. Contains top times 3. Okay, let's try again. And it's working away. I could make the iteration more efficient. Right, the calculation of next states. So while that's running, oh yeah, it's probably going to time out. I think we time out at 30. Okay, so robots, we change the value of R. And then map move area. Do we want to use a set of robots instead of a list of robots? I don't think we do. Do we want to use a set of positions? I don't think we do either. But maybe we want to use a separate list of positions from velocities. I mean, that's minor. That's not like algorithmic anything. Wait, we're still getting 250? Oh, no. This timed out. Yeah. Okay. So either our heuristic doesn't really work and it's not finding anything, so it's timing out, or wait, what do we call this? Let's call the 50 tolerance, or I know offset. Let's call it off equals 50. So bot minus off to bot plus off should contain top times 3. Oh, no, I don't want to be evaluating that. Let's cancel. So either our iteration is slow, or um, this filter wouldn't catch the tree. I guess a tree has a trunk, and the way I'm writing this, let's draw real quick. So we have AOC 2024. Okay. Roughly, what does the shape we're looking for look like? Oh boy, I don't like how this. I gotta calibrate my pencil to draw. But it's a triangle. If it's purely a triangle, then the bottom half would be triple the top half. But it's not just a triangle. There's a little stem. So maybe we're looking for roughly double instead of triple. And in the worst case, let's think about that interval. Let's just try that. Let's try that real quick. But in the worst case, this would work if bot were or top. Let's say it's 100. Bot would be 400, and minus 50 is 350. So it's 150. Would work with 300. This would work if top were 100, or top were all the way up to or 150 to 200, basically. And okay, like I did get something. Let's take a look at what it printed. Oh, I printed a lot of those partial search states. That doesn't look like a Christmas tree to me. But maybe it's a start of one, and it shows up after that. So let's just take a look at it. Okay, it is shaping up into something. Is my Christmas tree sideways? Okay, well, let's go up until that point. So this is state 65. Oh yeah, this is one we'd seen before. Mm. Okay, that's not promising. But I guess this is a case where the bottom half does kind of have roughly twice the top half. I don't believe that. Okay, I need to double check what my quadrants actually are. Um, and let's move this. Right. Well, ratio fits. So if ratio fits, look at a little print line. Returning ratio fits. Okay. This could be like a drop while ratio doesn't fit, and then we go from there. Let's change our offset a little bit. 25. We'll reread the problem. We'll check the quadrants that we're using. What is our top half? 0 until 50, 51 until 101. And they're both 0 until 51 on the Ys. Okay. I have no idea what part 2 means. um, it's a Christmas tree. It looks like a little pine tree. But Okay, so let's try this again. And we're not going to take just one. Let's take, I don't know, let's take four of them and see if that is promising. But, right, we gotta wait for that to run. Okay. Okay, so we have four little Christmas trees. Oh, wait, we only have one thing. We're only printing one thing. This is the old thing, right? Because this is, oh, state number 34,000. Okay, interesting. What are we doing here? So we do zip the index, keeping mind of the state, or yeah, the state number of seconds passed. If the ratio fits, we print it, and that should fit in the filter. I just don't know why we have so many ratio fits that aren't printed. Right, that's what it's telling us. It was printing all of those because the ratio fit in each of those cases. Oh, the ratio shouldn't fit in each of those. The print line's just running whenever. Oh, that's because of this. I never delete that line. Okay. So let's take 10 cases and print them. 10 might be too many. Yeah, 10's too many. Let's go back to 4. That did run to completion, yes. Okay, that failed to validate the worksheet. Let's just take 2. 2 such that it's roughly twice in the bottom compared to the top. Let's have my original roughly 3 times in the bottom. Okay, well that runs. So we have 2 examples. Hmm. State 14073 and 3670. Okay. What do those 2 numbers have in common? Is one a multiple of the other? So we have 14073. Actually, let's do this in Scala. What was it? 14073. And let's check modulo. Let me try to divide it by the first state that was like that, 3670. Or maybe we get the LCM. Okay, so one isn't a multiple of the other. But maybe we should search by least common multiple. Hmm. Okay. And again, this is this is something, but oh, hold up. What if what if the image of the Christmas tree appears in this sort of box that we have going on? So a lot of the top is empty and a lot of the bottom is empty. And that's the case that we're looking and that those are the cases we're looking for. Because honestly, I don't even know why this passes my filter, right? Because we had top had 167, bot had 309. I don't know where the midline is, but I don't really feel like the bottom half has roughly double what the top half has, right? Yeah, check if multiple number in a row. Check the counts in a row. The first thing I did was check if like we might have like three side by side, like vertically or horizontally, like forming a trunk. Um, but actually, it's worth noting. Yeah, I like the idea of checking rows, but I also like the idea of checking, roughly how many are in this top and bottom, like thirds, and if they're roughly empty and the image is supposed to be in the middle, I can kind of see a ratio going on here, right? Where the top is thinner and the bottom is thicker. Can you see that? The top's thinner, the bottom's thicker. I'm seeing diagonal lines here. I think the Christmas tree is supposed to appear in this box. So that's why my heuristic can't quite get it. Okay. So this is line 228, right? 190. So there's 38 until that border. And I'm gonna assume maybe those are solid borders. So if we have two lines that are solid borders, so one roughly 28 down and another, what's that, 260 to 292? Yeah, we could say 25 and 25. So the bottom and top quarter should be mostly empty. What are the elves smoking? I don't know. And I'm just gonna double check the problem description before I move on. Very rarely. Okay. Hmm. I know what I want to do, and I'm gonna do it. You saw part two as a what? It's not the first time where part two has been an image. There have been, I think, at least two where you have to draw like letters or something using the image, and then the letters that you draw are the code that you enter. So I was thinking about the theme of Abna code this year, and so each puzzle has a reference to a past Abna code puzzle. But each puzzle also like has a year associated, like with the time travel and whatnot. Like do the admin codes not happen like in sequence year after year? I'm trying an approach, not sure if it'll work, but let me know if you want me to share the approach theory. Um, yeah, I mean, I think I'd like to hear your approach. I'm gonna try. I have an approach in mind to try already. And if I'm not feeling like being spoiled, I won't read the messages. But I'd be curious. So let's change this. And in fact, let's just copy paste, keep this. I'm kind of partial to that. I want to be able to see that image again. So let's say top quarter. Let's just get all the y's. So val y is equals s dot map p dot y. So I'm gonna try checking that there's mostly nothing in the top quarter and bottom quarter. Val top quarter equals I don't know. Let's take 0 to 25 and bot quarter 78 to 103. Yeah, sure, that works. And then we count each of those. So top quarter contains, Copilot's got my back, knows what to do here. And if top plus bot is less than, let's say 20. It might be like a last few bots scrambling around, but let's just see how that starts to shape up. Now let's just take 1 and print that. Oh, this is taking a while. It'd be nice if I could find some sort of ratio. Multiple where this start to happen. Oh no, we didn't find anything. Okay, it was never the case at the top quarter and the bot quarter. Let's subtract 5 from here and add 5 to this case here. So it's narrower. We're gonna count how many are in each quarter, and let's print that. Okay, so mulgars. I'm going to test when all numbers are contiguous in a shape using the folding algorithm from the plants problem of the previous day. Flooding algorithm. Okay, yeah, I was thinking about something like that. My first attempt at finding a block was, well, it was a half-assed attempt, but I didn't find anything. I'm assuming when the trees form, all robots are together. That's like a decent assumption. It might be like a solid block, but like it might have holes in it. So I'm not completely sure. I'm just thinking I need to print the entire map every iteration and find the one that looks like a tree. Well, I tried that for 100 iterations. I can tell you that much, and none of them looked anything like a tree. And these interesting looking iterations came after 14,000 and 3,000 respectively. So you might have a lot of iterations to look at. This one can't be brute forced. It can't be solved in an LLM. How about that? Yes, the answer can be over 100. I found that number 65, there was something that was vaguely interesting. They were starting to all kind of line up in the middle. But that's the only interesting I found under 100. Maybe I should search multiples of 65. Right, just multiply my velocities by 65 and do that. Oh, this timed out. Okay, well, this approach doesn't really work. But let's look at those lines. Let's look at those line numbers. We got to calculate it exactly. I'll say when the top line is solid, I'll call it good. It seems like that The tree, I don't know if it's going to be solid or not, but this top line, I think it's pretty likely that will be solid. So we have 83 to 120. Let's do it this way. 83 to 120. This is an inclusive range. Let's get the size of that. So there are 38 empty rows. So the 39th row should be solid. Okay. Maybe the tree needs to be shaped like a previous year's calendar. That'd be fun, wouldn't it? Like the very first year, actually. Um, which I don't think 2015. Yeah, straight up triangle. Possible, possible. Okay, okay. Let's stop stalling. Let's do our new approach here. Um, so I think now we want all the positions at y equals 39. So s dot map p dot y, or no, we filter. Yeah. Well, let's map to take just the positions. Dot filter y equals 39. Rather count that. And if the count of that is equal to our area.width, is that going to be off by 1? I am so scared of off by 1s. Half of my library is created just to avoid off by 1s. Okay. So if row 39 is solid, or has 39 bots in it. In fact, hold on, I'm going to cancel that because I'm kind of paranoid. Let's do greater than or equal to 39. Or no, not greater than equal to 39. So y at 39 is greater than or equal to area.width. Let's just give it a little bit of wiggle room, just in case. Why are there two evaluations? I don't like this. Oh, if the tree is symmetrical, well, yes. But the thing is, I worry about that because if the tree has holes, if it's not solid, then it might not be symmetrical. But actually, good point about horizontal, like symmetry. I was thinking about like top half and bottom half, but yeah, right half and left half should be mirrors of each other. Hmm, that is good. It could be completely symmetrical. That'd be a great way to find it. Eric might be being devious, and maybe it's not. But if it's roughly symmetrical, could check that. Could filter where like left half and right half have roughly the same amount. But that's kind of like what I was doing up here, just checking number ratios. Failed to evaluate the worksheet. Timeout reached. I wonder how far we got. I mean, surely we got past 14,000, right? I'm gonna add a lot of wiggle room just so we can see more interesting images. And you know what? I don't even need the full count. Hold on, cancel that, cancel that. So instead of that bit of code, we are going to filter. So S is an iterator, right? No, we're gonna make it an iterator. So map to P, filter Y, and do dot size is greater than or equal or dot width minus 50. That way we don't necessarily take full count. Just check if it's shaping up to be larger. Okay. We'll run that. And that should... Oh, no. Oh, that just doesn't compile. Size is not a member of iterator? Hmm. Okay. Let's do it on the list then. Okay, still lots more wiggle room, so it should find something, right? Unless my row value is incorrect. Hold on. 39 is wrong. It's going to be add 38. Because our 38, there is an off by 1. I was so worried about that. Okay. We cancel that, and now, I don't know, we try to run again. Mulgars, how's your symmetry approach working? And Michael BC Gamer, what are you thinking for this? Let me, while that's running, oh, it failed? We reached a timeout? Really? At y equals 38. Let's just look at our scratch again. So this here, 190 would be y equals 0, right? So 228 would be y equals 38. Okay. Zombie Cho with a raid. Welcome, welcome. Did you finish? I've tried a couple heuristics for finding the tree. I haven't found it yet. And the latest I'm trying... So I found some semi-interesting images, and it's shaping up as if the image is in the middle, in a frame, in a square here. So I was going to look for an image such that this line here is solid-ish, but apparently that's not working. So maybe I'm wrong. But one way to kind of here see if that even makes sense in the first place is to check the ratio of the. Let's just take 0. Okay, check the ratio. So how many robots do we have? And what is our size? Brett says I'm on a pretty good zombie chow. Okay, zombie chow. Thank you for that. Mm. Okay, I'm told I'm on a good track. Then I believe it. It's a square in the middle. And if it's not a square in the middle, you know, I don't mind being spoiled on whether or not there's a square in the middle. 500. Yeah, 500 out of 10,000. I mean, geez, 500 is like a 25 by 25 block if it were solid. And if you unfold that into a tree, that's like 50 by 50. The tree itself is like 50 by 50, which would make sense. But okay, let's look at this. So it's like it's like 38 above, 38 below. The tree itself is going to be roughly 50 by 50 in size, so it makes sense that's a square in the middle, right? Um, yeah, I think the LLM might struggle with it. That's what someone else said earlier today. I mean, if you told the LLM what your approach was exactly, it could help you with implementing that approach, I suppose. Um, oh, did this print? I want to see. I want to see my tree. Oh, right. I need to take at least one. Um, oh, no, this didn't work, did it? Taking P, at y equals 38, and there are at least 50 of those forming the frame of the image. Um, oh boy. Yeah, okay, that's not working at that line. What's flexing me is that it's not even generating one of these. Like, how many are in this? I'm gonna do this real quick. I'm gonna take that string, um, and we're gonna count. Let's count. Hold up. Okay, so we're gonna take that as a string, and we're gonna count the number of pound signs. 27. So 27 out of 101. Okay, let's just change our search so we could at least find stuff like that. Let's say greater than or equal to 30. Oh, I'm gonna say 25, just so we can see if it's able to catch that particular image. If it can't catch that particular image, that tells me what my y-index is wrong. In which case, I guess I debug that. Now that one was at like either my y-index is wrong or this is just horribly slow. That's the thing. I'm not writing this in such a way that I can give myself that insight. And why is it running twice in parallel? Okay, state 65. Yeah, I remember state 65. Actually, let's take a look at it again. So I'm gonna copy this worksheet output, and I'm gonna move to Scratch 2 because I am kind of partial to my Scratch 1 that's developing. Okay. So we can take the state 65 and use it to help us iterate through these cases faster by multiplying our velocity. So we could take all of these velocities here, because state 65 is the first interesting, like potentially interesting bit, right? And we look at all the vertical velocities of all of these, and we take the least common multiple, or like we look at how many times each of them would take to get back. So the period of each of, um, yeah, I assume that these want to eventually end up back here again, right? So we look at the y period of each of those. Um, and yeah, we take the least common multiple of the y periods. And once we have the least common multiple of the y periods, we want to iterate that many steps at a time from 65. Yeah. Okay. Okay. We have a new approach. Or at least we have a more efficient approach. Yeesh. Okay, cancel this evaluation. Drop that back to 0 for now. Um, this quarter approach, I did really kind of like that. I guess that doesn't work. I'll just keep the code in case I come back to it. So we take our states. I just want to get all those points. Well, let's just take state 65. So states dot drop 65 dot next val interesting states. I know. Okay, and then we take line state, get all the positions, and let's get all the y values. The velocities rather. Wait, hold on. First we filter them for position at y equals 38, right? And then we want to get their y velocity values. So map velocity dot y. Let's call that v's. Now we want import alc.math.lcmn. So yeah, LCMN of v's. Hold up. Just gonna put a take 0 in here because that is messing with me with my evaluation time. And how does our LCMN work? Okay, so the second error variable is, and this is a list of ints. Great. Use that tail. Let me pass that in. And that's gonna be our period now. Period, our post 60 period, or post 65 period. And it's slow. Wait, what is slow exactly? Getting the 65th state? Oh boy. Really? Least common multiple is negative? What are these values? Oh, wait. Some of these. Okay, we want to take the absolute values of these and then take the least common multiple. Oh, hold on. You want the periods of each of these with respect to 103. Okay, so we take the fees. Fees.map. LCM of area.height and V. Or no, we don't want that. We do want area.height. Hold on, I guess we do want the LCM because we want to know how many periods it takes for that. Yeah. Call that P's for the periods. And let's start there. while that's happening, S1 doesn't take long. I'm just gonna comment it out anyway. I want to see what my periods are. And then once we have our periods, we want to align all those periods. So we do want to take the least common multiple of all of those, right? So when all of those end up back in the line, oh, okay. So period is going to be p dot head and p dot tail, LCMN of that. And it might be the case. I might just try this. Val ends to equals period plus 65. I'm going to go off a hunch. I will try that as an answer. Okay. So, wait, which is which? That's the period, 36. Why is ans2 not evaluating as something? Well, I mean, let's plug that in. So 866, 5, 5, 4, 7, 3, 6 plus 65. Okay, it finally went. Okay. We'll try this. That is too high. Well, we have an upper bound. How about that? Uh, that's really the least common multiple of all of those. Oh, wait. Why are some of these periods negative? Yeah, I forgot to do the absolute value. So v dot abs. Okay, let's try this again. Now I'm not gonna be able to submit. I should spot checked that first. Oh, Zombie Chew, you'd asked how I'm searching for it. Well, I know that state number 65 is the first state at which the bots sort of start to line up in like the top and bottom boundaries of the frame around the Christmas tree, right? And originally, I just started to search for states such that 38 has a lot of these, but this was going too slow. So I'm speeding up my approach by taking that first state, number 65, where they start to line up, and calculating the periods, assuming that we want those all to end up back in that same row. And then I'm going to multiply my velocity by that so that the search goes faster, and we only search for states where they're already in that row. Okay, so even though this is positive, I don't think the periods have changed. And that's unfortunate because that means I can't speed things up this way. So after this many steps, they are all back in that row again. It could be the case that some of those are meant to go into the other row, or not all of those. Like one of them is in there accidentally, and it could screw up my calculation. So I could go back to looking for states that have some number of these, and I could use that to calculate the period. So if we change our threshold here, let's say there's more than 15 in that row, then we search for 2 of these. So I'm going to take 2. Um, Then we could use that to calculate a period to speed things up. It will look exactly like 65. I don't think it will look exactly like 65 because, well, those positions will be in the same row. Like the x period for one might not be the same. So they'll all be in the same row, but not necessarily everything else. We're on TV. You're mad about part two, but you did it anyway. Hmm. What makes you mad about it? I mean, it's a weird one, isn't it? Okay. Yeah, welcome, welcome. Congrats on finishing GG. So what do we have here? We should be printing two states that have a bar. Let's take a look at this. Let's bring a copy worksheet output. What? Would this not evaluate? Follower goal. I didn't know I had follower goals, but hey, I have 300 follows. Thank you, Jeff Irwin, for the follow. Okay. You have different X and Y periods. You are mad too. I cheated and found what people did. I didn't copy any code or anything, but I was curious about how people solved it so fast. I won't share to spoil anything unless you want. I don't mind mild spoilers. I don't mind like mild little nudges. But I can tell you what I have so far is that, well, hold on. Here, I'll show you where we're at. Okay. So I've been printing certain states of interest, right? So every now and then, these all sort of start to align here in the middle. So that tells me that the picture will be, in a small little frame here with borders on the top and the bottom. And what I'm looking for is these top and bottom borders. Now, searching that on a step-by-step basis didn't quite work for me. It kept timing out at 30 seconds. And I refused to, I refused to just let that run. So I'm basically taking a couple candidates for things that have them sort of starting to align, and I'm looking for a period. So we have 168 and 65. So I'm going to move multiple steps at a time. So 168 minus 65 is 103. Oh, 103. Okay, I guess we're moving 103 at a time from... Wait, really? What were the velocities there? I guess one of those has a 1 velocity, but I'm not even enforcing that all of them end up back in the same place. But both of these look sort of right-ish, right? Okay, so I'm going to move 103 steps at a time from frame 65. You're right about the frame. Thank you. Thank you for confirming that. That does ease my mind a little bit. Okay, so let's get back in here. Line state 65. So we're going to start with this line state. Geez, what was our states function? Def states. So our state is just a list of robots. I want to do a next function. So def next state is a list of robots. Bad Nintendo, thank you for the follow. The answer isn't astronomically huge either. Okay. You didn't find the tree by looking for the frame. I mean, there are multiple theories, right? Someone talked about symmetry, and then there's the idea that maybe you just look for a block of things that are occupied. And I guess basically we move each of them. I know it's wait, what do we have? So we start with the positions. Wait, what's going on here? Is our states iterator incorrect? So if we iterate starting with the states, oh, right, we're just modifying the velocity. Let's introduce a factor here. Step int. So let's give it this. Well, I guess we don't mess with the step there. We can mess with the steps at another point. Basically, we just take this here. Each robot we map state.map, and it's going to be r.move within our area. And that does the wraparound. Yeah, okay, so we'll run with that. So our line state, let's start at the line state. So iterator.iterate. Well, we're gonna modify this. Let's modify this a little bit. We want to change the velocities. So .next, we're gonna map. So for each of these r's, we're gonna take velocity and multiplied by 103. Wait. If we multiply the velocity by 103, won't they all end up? No matter what, won't they all end up in the same? No, I guess not the same spot. If you move up wait, if you move any direction. Oh, okay. So the x's change up. It will have the same vertical direction if you do 103. So that's why this can't be a square. Okay. Yeah, and then we wait till the x's line up, basically. Wait. But in that case, scratch. So not the scratch. In that case, there will be text here, right? Like this might still end up being, that's not gonna be a solid frame. There's no way that's a solid frame. Unless a bunch of bots are just overlapping, which I don't think that's the case. I mean, it could be, right? 103, they'll be back in the same vertical position, but they'll be in a different horizontal position. So maybe some of these are multi-bots. Maybe. Okay. Well, anyway, we're gonna iterate from our new line state. Actually, we're using that elsewhere, so we'll keep that value. I don't know. We'll just call this our start. So we take our line state. It says increase velocity by 103. And we iterate from start with next. And I guess we'll just print each of those. So let's take our printing code down here. Yeah, so we have start, we have next. You want to zip with index. And that index we will need to multiply by 103 and add 65 to. Yeah, okay. And let's just make this not run. And this will print a bunch of images. I wonder, so this is the first time here on the right-hand side. This is the first time we found interesting bits, and I'm keeping that. But this 14073, 14073, let's subtract the other index, 3670 minus 3670, 1403. Okay, and if we divide that by 103, do we get something 101? Interesting. They were 101 times 103 away. Maybe that should be the period at which well, hold on. Are those identical? They have to be identical, right? Those are identical. I mean, obviously, 101 times 103 is an upper limit. Yeah, right. You can't have more than that many states. They're identical. Of course, they're identical. Okay. Um, yeah, and did we just search every multiple of 103 inside of that? No, no, I think we don't search every multiple of 103 because the boundaries aren't right. I think we search every multiple of 101 between those two states. What I should do is have a function that tells me the state at a certain time and just basically like multiplies velocity, whatever, rather than doing this iterator thing I'm doing. But anyway, let's see. This should have run by now. What are we printing? This. Did it not run? Did it not evaluate? Oh, whoa, whoa, whoa. That's infinite. That's infinite. um, okay, let's take one of these. Zip with index dot take 101, starting from that 65. Oh, and hold up. That earlier number, 3670. Okay, let's explore this. So 3670. Let's take that minus 65 and let's divide that by 103, 101. Yeah, 3670 is much too large. So what's 101 times 103? Why didn't I think of this earlier? Yeah, there's like a maximum period. Okay, so after that many iterations, it starts repeating. So we only need to search within the first 10,000. 10,403. This was like 35 times that. Wait, no. 3,670 minus 65. This is 101 35 times and 103 35 times. This 3605. That's not exactly 101 times 103. There's some mathematical insight that I'm missing there. I'll just let it fly over my head. You're done. The symmetry did not work. Oh, good. But you found another approach. They do not render the tree in the center. That's nasty. That's nasty. Eric, you still here? Okay. What was I doing? This didn't print. Right, because it's infinite. So I can take at most one of them. I don't know how many threads I've run in the background, so I'm just gonna restart VS Code. We've limited to 101 cases, starting from 65 and iterating 103 at a time. But maybe we should start from 65 and iterate 101 at a time. We'll see. So we're printing all of these. There are roughly 100 of them. I'm just going to scroll through. If this doesn't work, I'm just going to flip 103 and 101 and scroll through those. So I have 200 to check visually. That's not bad. Are we supposed to do this manually, or are people using CV or something like that? No, no computer vision necessary, but there is like boundary detection. You can detect like the boundary. I think the image has a solid boundary, but maybe it doesn't because I wasn't finding that. Okay, so let's look at this. Match to. All right. I'm gonna zoom out a lot. And if I don't see anything here, whoa, that looks weird when it's zoomed in so much. What's going on? Okay, we are looking for a tree-like thing. Wait, there's some weird syntax highlighting here. Mode, change language mode, and it's just text, plain text. There we go. There we go. That's better. So this is a manual check, but it's a smart manual check. Look, they all roughly line up in the middle. Oh, that's close. That's close. Not quite, but that's close. State 74. So that means 74 times 103 over 65, or plus 65. State 74. Remember that number. And look at that. You can kind of see the two triangles happening. You know, if you squint while reading these, I'll catch up on messages in a sec. Mhm. There's only 100 to check. We're almost to the end of them. Okay, so 74 was close. All right. And this one's good old number 65. Now, let's zoom in on 74. Let's zoom in on 74. State 74. I'm going to catch up on messages real quick. Bulgars did not do it manually. And you have some sort of insight. I'd like to know what that is. Could have been worse. I was afraid there was going to be an ornament on top of the tree to make it harder to detect. Yeah, well, good to know it's not there, but I was worried about that too. This is as close to decoding satellite PPV channels by squinting. No squinting required. You'll know it when you see it. Okay, I believe it. I mean, squinting kind of tells you if you're sort of. Oh my god. Oh my god. I hate this. So I'm realizing here that the frame doesn't go all the way across. I should have realized that earlier. Um, It's a square. There's a square around the tree. Okay. Yeah. Okay, so this is state number, this is after how many seconds? This is 74. 65 plus 74 times each of those 74 steps is 103. So this is state number 7687. Um, okay, neither the x's or y's are quite aligned yet. Um, but so wait, everything from the 65, I'm kind of surprised. What did the 65 state look like? So the very first state here, it had solo and state 0. Okay, I'm surprised that this here isn't the same number as this, right? If we were iterating 103 at a time, wouldn't all of these end up back in the same row? Am I wrong there? Danish Khan, welcome. This is this is day 14 of Advent of Code. I can drop the links to the puzzle for you. I don't know if you're doing, you must not be doing Advent of Code, but here it is. I'll let you read that. But basically, we have a bunch of robots moving around. At some point, they form a Christmas tree image. And to figure out at which point. Okay, this is step number 7687. Okay, this thing here, 103. Why is it that moving 103 steps doesn't result in all of these being in the same vertical row? Or in the same row, right? Vertical row, that's a column. Um, right, like no matter what y is, if y is 1, after 103 is going to be back here. If y is 2, same deal. It's always going to end up back here. I guess that's why, are 101 and 103 both prime? I think they'd have to be prime. Well, they have to at least be mutually prime. Um, we can just count this, and we could look for that. So there's an approach. I feel like we can do a new iteration, though. Do we iterate from here? Like, how many 101s is this? 74 times 103. Let's take 74 times 103. Divided by 101. Yeah, okay, that's not some equal. I think 101 and 103. Well, I mean, obviously they're like mutually prime, so that was not never going to happen. Um, can you print all output into a text file and search certain phrases? I that's basically what I have here. Each of those may have a different period, so they may not all be the same, all be there in iterations of your multiple period. But my multiple period is 103, right? And they go off the edge and wrap around. Like each of those have a different period. True, right? Like if it is moving up 2 at a time, its period is going to be 100. It's going to be 206. Yeah, okay, right. Yeah, that makes sense. That makes sense. Yeah, it's going to be 102. um, but the period is always going to be a multiple of 103. Let me just, I just want to check that those are prime. I think they are prime. Let's go Wolfram Alpha. Is 103 prime? Yes. And is 101 prime? Okay, they're both prime. Yeah, so their periods are all going to be multiples of 103 and 101 in the x direction. So if you want to end them back here, it's good that we're stepping 103 at a time. Is 101 times 103 really an upper limit though? It's not an upper limit. Maximum period possible. Yeah, I guess 101 times 103 is not an upper limit. Mm. Okay. Well, let's go back to our little drawing board. And see what we were doing here. Thank you for that, by the way. What is crit? Get me out of that dumb rut. I mean, maybe I don't want to be spoiled, but I do want to be told if I'm saying something dumb. Hmm. Okay. So we multiply by 103 because that. Mm. And then I guess it's the first time the x's sort of line up, right? So I think from here, we want some multiple of 101 ahead. So I think from here, from this point, we actually iterate by 101 times 103. So I don't know. Our first nice pick. Well, first nice pick is going to be states that drop. Well, no, let's do this search here. Let's give this a name. Uh, step 103. Okay, so we're stepping 103 at a time, hence the name of that. And we're gonna take you don't need that printing here. Now we're gonna take step 103 and we're gonna drop the first 74. Next, this is our first nice pick. First nice pick is there. I promise this all cleans up well later. And then we have 7687. State 7687. Okay, and now from here, I know, start to, we are saturated in names here. Start to, it's gonna be kind of like this, but now we've already multiplied the velocity by 103. Let's multiply it by 101. And we're gonna iterate from there. Is this right? We can check very, very soon if this is the right idea. Okay, and we're gonna do basically this code. I should really just have a way to like pass in the state I want and jump directly to that instead of doing this repeated iterating. Sure, we'll take one of those. We might not need one of those, but... And we'll draw them all. Okay. This is new, right? So state 0, whoops, should be our first nice pick from earlier, but it's not. It's not. Hold on. We have a bug. So start 2. We didn't use start 2 here. Okay, we want to start from start 2. Okay, namely 7687. So we copy the worksheet output of this. Search for state 0. Nope, that is still not. Did we actually get new worksheet output? I'm just gonna wait for that to run. So this should start at start 2. And start 2 is the first nice pick. We should just do like a draw function for like all this stuff. I just want to verify what this one looks like, this first nice pick. So area.draw p if LPs equals first nice pick. We'll just get all the points, put in a set. Okay, let's see what this looks like. Yes. It was state 74, right? So you drop the first 74, which is state 0 through 73. And the next one is 74, or 7687. It says it evaluated this. There must be an error here somewhere, missing parameter type. Where? Oh. So first nice pick. Oh, hold on. I see, we're using line state here. Okay, so that's _1. Okay, start 2 should use first nice pick. I think we can comment this out. Okay, we just started at the wrong spot. Okay. Yes, there we go. So that was state 0, the first nice pick. And look at them. Look at them. They're all like squarish. And we are iterating like 10,000 at a time here. We will know it when we see it. Ho, ho, ho. I do like this problem. It seems a divisive one. Look at that. Hold on. I think we can probably scroll faster, yeah? Okay, I mean, we can scroll through these. It might not be in the first 100 or so multiples, but what we do after this, we're done with the scrolling game. If this doesn't work, now we can just iterate on this and do our search within this for something that has a proper frame. So we just need to figure out the frame coordinates and yeah, we search for that frame. So back here, val, more nice states, or rather a def here. So we don't need this printing function, but we do want to take more nice states. And we're gonna, let's just straight up do a find. I don't know what this is. Wait, we want the thing earlier that I was looking for a line. Almost there, I know. 38. Oh, where is it? Okay, yeah, something like this. So what is this, the top border? I'm gonna manually check some of those. Oh, yeah, let's manually check this size here. So these are clearly the corners. Okay, so the width is 31 and the height, let's look at the row numbers. So 210, 178. So 178 to 210, that size. Okay, and the height is 33. Okay. And I think we want to know where the left side is. So let's take the size of this. $32. Okay. So we have the area where it's supposed to be. Let's define that. Val, or where are we? Nice picks. More nice states. Okay, so val target area equals, hold up, what is the width? Let's take an area. Val A, that's the right size. So this is the width, right? 31. 0 until 31. That should be the width. And then the height is 33. So 0 until 33. And A dot shift by, hold on, we don't have a shift. Okay, whatever. I guess we do 38 val left. Left is going to be, wait, what was the width of this? 32. Left is going to be 32. Val top equals 38. Val bot equals top plus 33. Yes, yes. Oh, I hate this so much. Top 2 bot should be size 33, right? Val right equals left plus 31. val w equals 33. We're just gonna put in some asserts in here because I don't trust my off by ones. So the width is 33. Val height is wait, no, the height. The width is 31, the height is 33. And we have an area constructor that does take top bot, left, right, right? Left, right, top bot. Okay. Here we go. So we have an area constructor, top equals top, yada yada. Copilot can do this. And then assert a dot width equals. Okay. We have a target area. And now we take our nice states and we count how many are in the target area. And when that's 500, we are good. So more nice states. And then we filter dot filter. So again, starting from, what was it? 7687, iterating by 103 times 101. So we take all the positions and then we count how many are in the target area. Val C equals p dot count target area that contains. And then if, I guess we just do, our filter is when C equals 500. And we're just gonna find the first case like that. And to get our answer, whoops, val image, I'll call this end state. Just stop there. And end state here, I guess, is a tuple, right? So end state dot get dot underscore 1 times 1043 plus 7687. Okay, it's a sloppy worksheet, but this should do it. Oh, no, we want underscore 2. Target area. Oh, right. We do return that A. Okay. What is this? That's code we didn't want. We don't want this either. Val hands 2. Where did we put that? I am so lost in this file. There's too much code. There's something wrong with this. An assertion failed. Good. That means we did this wrong. So bot equals top plus 33. Wait, no, top plus height. Okay, let's say if the height was 1. The bot should be the same. So we have -1. And then left plus W -1. I don't need this top and we don't need this bot. Or hold on, we do need the top. We don't need the bot and right. Okay. Those assertions have passed now, and now we're calculating the end state. It is evaluating. But I think we're there. I mean, while that's running, I could also draw it. Brute force hits hard here. Hey, it's not exactly brute force, because I'm iterating 10,000 states at a time, so I'm not checking every single state. I could also just do some math on like the individual points. What? Maybe, I mean, if I knew where. Okay, this search is taking too long. Maybe c equals 500 isn't quite it. The left should be 32, right? Because this is 0, index 0, 32. And this is line 38. This is column 32, line 38. So our target area, this should be correct. So top is 38, and the left is 32. And it is the right size, the right width and height, according to what we calculated. Maybe c equals 500 is not quite, how many bots did we have? I think we had 500 bots. But I should be doing robots.size. Okay, let's comment out that search real quick. So robots.size. Okay. Hmm. So this is what we are iterating over, right? This is state number 7,000. And we iterate 10,000 at a time. And those change up. I guess I could take that state 7,000. Do something with it. But we could look at the points that are outside of this box and see how long it takes for them to get into the box. Width equals 331. No, the width of my inner box is 31. And yeah, the width of the outer thing is 101. Okay, let's talk about what I was doing here. Right, so we found a nice looking state, 7867. We're iterating by 10,000 at a time by multiplying the speed, right? Wait, I wrote 331. Oh, okay. Okay, thank you very much. Thank you very much. Good eye. Good eye. I appreciate it. Okay, so we let that run. And while it's running, I do also want to see this eventually. So let's draw a print tree function. Well, show image. So state is a list of robots. And we basically take, where is it? This. I just want that as a function. Failed to evaluate the worksheet. Oh, hold up. Now it's saying there's an error. Okay. Let's finish this implementation. Um, val p is equals area dot draw p. Okay, so we have our answer, and then we're also going to do a show image. Show image and state dot get that underscore one. Let's let that run again. Evaluated, we got an error. Oh, wait, this is a def. Okay, more compile errors. Get that out of the way. Your frame is in the center in both dimensions? I don't believe it's in the center. All I know really is where the top left is and how wide and tall it is. I suspect it's not in the center because Eric wants to be devious like that. No, it timed out. It timed out? I'm searching 10,000 at a time. I don't think it's that this is too slow. I want to say there's a mistake in my code that finds this. Wait a second. We don't need to do like make this a set and then count. We can make this more efficient for one. Yeah, like we can say val c s. Let's just take an iterator of these. Iterator map to get all the positions, and then we count how many are in the target area. What is printline doing? That prints the image after it. So it takes a string. This area.draw draws a string, and it prints that. This draws like a grid with line breaks and everything. But he went crazy with a new Scala 3 formatting. Yeah, they made it Python or Haskell. You got 10x programmer in house. Thank you for the follow. Okay, so this is let's try it this way. This is slightly more efficient. I don't think efficiency is necessarily a problem. Maybe all the robots okay, all the robots do end up in that center frame, right? They must. I don't want to live in a world where the answer doesn't have empty space here outside of the frame. It could be that I'm searching from the wrong place. Right? We searched starting from 7,000. We found that 7,000 by iterating from 65. Wait, okay. Okay, you're trolling. You're trolling. Maybe reread the description. Thank you. Thank you. I will reread the description. I want to be in on this joke. I want to know what I'm missing. I want to laugh at me too. Just kidding. I won't laugh. I'll cry. Hmm. Very rarely, most of the robots should arrange themselves into a picture of a Christmas tree. Most. Fucking most. Okay. Most. Well, I mean, most. Like, this one's most. Most of those are in a Christmas tree. Most of those are in a Christmas tree. Is the frame not solid? Okay, you know what? All I'm gonna check is that the frame is solid. We'll change our check here. Um, Screw this approach. So, oh, whoa, what's going on here? Okay, so we have a target area. Target area dot top gives us a line, right? Top border. Um, what exactly is a line? It's sort of basically a range. Okay, so top border dot points. And we want to check that all of those are in our set of points. So val p's, and we want to do that for each of the borders. Why are you iterating 10, 403 at a time? Because it's 101 times 103? Let me get back to that. Uh, that's probably a really good question. Do you want to know whether the frame is solid or not? You know what? I I think I'd like to know. So more than half. Uh, okay. Maybe that's too big. I do remember seeing a case that I put a pin in. Let's think about this. Let's go back to, yes, it is solid. Okay. Let's think about this. I have a couple things to think about. The 104 times 103 and the 35 case we were seeing earlier. 35 showed up somewhere. We'll get back to that. It's my REPL history. Okay. So, yeah, every bot has a period. Um, and well, it has a vertical period and it has a horizontal period. Its vertical period is going to be a multiple of 103. And I think I did that because I wanted these to have to all come back here, right? So I'm iterating over states where these return to the border. But that means these should return to wherever they came from too. Well, I mean, not necessarily. Like these, so multiples of 103 vertical, like somewhere in those multiples is going to be a state where they return back here. But these might move around. Well, I mean, these will, hmm. Yeah, every vertical period is going to be a multiple of 103. Ditto for the horizontal case. And I want to look for something that is, like, this must return here, right? So this must be, the number of steps past this must be a multiple of 103. Hence the 103. And ditto for the x's, right? Like the number of states past this must be a multiple of 101. Because for this to get back here, we must have, yeah, a multiple of 101. So it must be a multiple of both 101 and 103. Hence, right? My reasoning works there. Because for the border points to get back to their position, the thing must be a multiple of 103 and a multiple of 101. So we're skipping 10,000 states at a time. Nothing moves, but we can see, wait, You think nothing moves? Oh my god. Oh my god. Oh my god. Oh my god, it's the same image. Okay, you're right. You're right. Oh, my math is so bad. Okay. I did not see this earlier. Didn't I scroll through these and I scrolled through these looking for a Christmas tree. I didn't realize they're all exactly the same image. Okay, so wait. 101 by 103 is an upper bound. 101 by 103 is an upper bound. Uh, okay. Okay. Let's go back to this. I know. I'm having fun. Man, it is it I would say admin a code is more fun with people commenting on my mistakes. Uh I mean, for one, the sooner I get done, the sooner I get sleep, and having a code is always a low sleep month. And it's a bad feedback loop. Okay. Wait, what's going on here? Suddenly have type errors. Oh, right, right, right. Um, yeah, because we're not doing that anymore. And we're not doing this anymore either. Whoops. Um, Let me just comment that all out. What starts at 6 a.m. for you? Good morning practice. Yeah, I think I might like starting at 6 a.m. because then you don't have to be done in 3 hours for work. But then all day at work, I'm thinking about, it's only been one night, I think, where I've been over 3 hours, right? We're not to 3 hours yet. Okay, we give ourselves half an hour from here. Um, so this is the image 7687. How did we get there? We got to 7687 by starting at 65, which is the first interesting sort of image. You know what? Let's backtrack to one of our earlier approaches. Let's take a maximum of 101 by 103. It is an upper bound. How did I convince myself it wasn't an upper bound? Um, yeah, let's just take all the original states. And we were able to iterate like 14,000 before, so we can just brute force this. Um, and we can take our target area code. So we'll take this, but we're just not iterating on more nice states. We're just iterating on the original states. And this can just be an index where function. So states dot take area dot height times area dot width. Okay. And I guess states is a list of robots. Yeah, cool. Where was I? And we're gonna take dot index where. So given the state, um, did someone say whether the board is solid? Is it solid? Yeah, it's solid. Okay. There's a question of whether all the points are in the border. I think we'll just run this. We'll just run this. We're only iterating over 10,000. I think we can handle that within 30 seconds. And let's see. End state ends to right. We're gonna do something like this. Oh, this doesn't get the end state. This just gets the index. End state actually is just our ands since it's computing an index. So let's get the value of this. I hope nothing else is running that makes it slower. Get is not a member of int. Oh wait, states up take for one. We have weird compiler errors somewhere. Let's comment this out. So much commented code in this file. Not all points are in. Not all points are inside. Okay, right. It does say most of the robots. Oh, friggin' Eric. Okay, so we can do that. I'm just gonna delete this. Uncomment this. So we have a top border. The border is solid. Um. Oh, look, we got -1, so we didn't find it. So index where the top border is solid. We want all the borders being solid. So points that to set. We can just do for all. For all, it's in P's, right? So we'll just change this to go to an and. Okay, so all the borders of our target area must be solid. And this here is going to be our answer. Wait, 7687? 7687? No way. We've scrap this is 7687. Top border, all points of the top border of the target area are in the set of. We've already done 7687, and this is what it looks like. Have I heard the answer this whole time? I'm gonna put it in, but there's no way. Yeah, okay. This is just weirding me out. So our target area, top border points. All of these points should be in our set of robot points, right? Yeah. It should be a subset of our border um, of our taken positions. It did say 7687 is too high. Oh, wait, hold on. Index where? I mean, index 0 should be the beginning state. So 0 seconds, right? So index 1 should be the next state. 1 second. Index 1. It wants to know the seconds. What is the fewest number of seconds that must elapse for robots to display the Easter egg? Oops. And it did say 7687 is too high. Okay, this is supposed to be code that checks that this is that checks if the border is solid. And apparently the border is not solid. Right, so this gets a line from the top left to the top right. And a line is a line of points. So I can take those points that are in there, right? Yep, it's always still worth learning the code. If for nothing else, then it's. I mean, someone's got to be able to run the LLM. Okay, let's take a closer look at this. We are only taking an upper limit of 10,000. We know that 10,000 forces us to be a period, right? So we're iterating over all the states. Let's make sure states is actually what we think it is. Right, so states, we don't even need to map this. Just takes the original set of robots and we move those robots within the area, right? I do kind of want to start fresh with the clean worksheet. And I want to change how I calculate the next. I'm doing this like dot move. I want move to take like a seconds as an argument. So it's like after so and so many seconds. Yeah, so that is what I think it is. Each move is 1 second. I'm iterating over all of those. And we can absolutely brute force this because 10,000 is not too much. I'll just check for the border in some other way. It just weirds me out a little bit. Just make that take 0 for a second so that we can play with the worksheet. For all p's that contains, s is... Okay, let's test this. Let's just make this a set of points. And I don't know, this should not come out as true. Right, target area at top order points for all NPs. Wait, we have a double definition. Border points, BPS. Okay. My worksheet is too long. Okay, I mean, yeah, that is false. I just want, okay, I need to print this. So, end state, we're gonna make this a zip with index. Zip with index. So we have end state and end index. And we're not doing an index where, we're doing a find. So that should return a sum. And then we're going to show image of the end state. And I will see it for myself to that these borders. Actually, let's take a look at those borders. Print line, target area, that top border. I don't know. I just want to make sure I'm not going crazy. So here is our image. Hmm. Is there an easy way to say contains solid border? Unfortunately, not yet, because my area code only like gives you the border lines. Wait, it has an issue with this. Yeah, whatever. Uh, so let's copy this worksheet output and let's take a look at that. Oh, am I off by one? End index is 7687. I mean, that is it. That's absolutely a Christmas tree. Okay, I'm just gonna subtract one. I found that number 7867. Oh, am I just dyslexic? Okay, okay. 7687. That's it. Oh my god. Hey, there it is. There it is. We got there. Man, I've had a rough few days. But you know what? It's the weekend now, and I finally get to sleep and sleep in properly. Tomorrow night, we get to reset, break out of this cycle. Okay. I went from 1300 to 6700. Yeesh. Look at this. My delta times are just so bad. Oh, the last 3 nights in a row. Okay, the last 3 nights in a row have been too long. Do a leaderboard check real quick. Thank you, thank you. Thank you for the claps. I appreciate. I'm not alone here. Okay. Refresh this. And where are we? Have I dropped to number 9 yet? I'm currently 7 until Jan Pieter finishes, which I know he will, and take that back. And for day 14, 12th overall. I was 5th for part 1 and 18th for part 2. There was one night I had a really good delta time, and that's when I solved part 2 before solving part 1. Which I know I'm not the only one that did that, but how big is my frame? It is 33 by 31. We can take a look at that real quick, and then we're going to find someone to raid. And if someone already is searching for someone to raid, I wouldn't mind a suggestion. Width, or what did I say? W equals. Yeah, my frame is 31 by 33. Um, Everyone's frame might be the same size. I suspect that the left and top will be different for different people, but we know it's not centered. We found a solid bit, though. You know, searching for a solid bit would have worked. Right? But I was searching like down here. I was expecting the image to take up the full frame. It's easy to miss this. It's like so small, and it's off center. You try again for like different iterations of where the solid bit is. Okay. We are looking for someone to raid. Someone who's working on Avena code. Wait, Michael PC Gamer, you're still working on it? Oh, hold on. Let me mute myself here. I mean, we're definitely rating you if you're not done. Actually, we haven't heard from Michael PC Gamer in a while, so yeah, he's probably not in here. All right, everyone, say hi. Let's cheer him on. Oh wait, I want to see what people are up to. Oh yes, yes, yes. Please spoil me on what you did. Please spoil me on what you did. Let's do a quick review of those first. So zombie chow. Search for 5 horizontal robots in a row and just scroll through the images. Okay, okay. Not vertical. That's a. I would have been scared to do that brute force, but I wasn't really thinking about like how long it would take. You end up filtering on the state for a line containing which matches the frame. Yeah, that works. Zara, you counted components using BFS. And every time I found a new minimum, I printed the grid and the number of iterations. Interesting. Um, I want to see your code. You're gonna have to elaborate on that a bit. That sounds interesting. Right. Plausible to think it has some solid rectangle. I mean, I didn't think that at the start. I only discovered that by seeing, sort of like half-formed images. Did anyone just scroll? Okay, it's 10,000. You can't scroll through 10,000. I see black teep, same thing, but search for 6. Always easy to say in hindsight. Yeah, yeah. That help aside, search for clusters of connected cells with a robot in it. Like this here was my very first approach. I just kind of half-assed it and didn't try it for very long. Perhaps I should have continued with that. Um, I mean, I did all this stuff at the period, and I ended up just brute forcing anyway. Tower kick, okay. You just search for the largest connected component. That's a clever way to do it. And once the largest connected component was over a size, right, because even if it has holes, you don't have to worry about, right, because I was worried the tree might have holes in it. So that gets around that. I like that approach. And Icy Black Deep, I already had hard code for printing out the grid. Yeah, I can have that too. Horizontal gang. See, I did vertical to start because I was looking for a trunk. And I searched in the middle. Oh, that was part of the problem. I searched in the middle. Of course, it's offset. And 10x Programmer, you checked if no bot overlapped because I thought the puzzle was created. They painted it with only one bot per cell. Yes, check that no bot overlaps. Hey, that's smart. That's smart. It was a question I kept asking myself as we were doing this, was like, are there overlapping bots right now? Oh yeah, NX and Nomad did the same thing. I like that. I like that. This is a really fun problem. I like that there are so many different approaches. This is a this is the kind of thing that sets Avnet code apart from Leak code. All right, it's funky, it's different. You get a variety of solutions, and they don't just give you like write this algorithm. So I like that. Um, Great. Now we can all spoil Michael PC Gamer on like 10 different ways to do this. Let's start a raid. Raid Michael PC Gamer. Thanks everyone for the help debugging, preventing me from doing stupid shit. Yeah, thanks for sticking around and sharing your solutions. Oh, I'll just drop this here. I might want to see some of your like code. This could be after the fact. So if you want to share code with me, you can post it there in my Discord. Great. Let's start the raid.